Thank you so much for having us. We're really excited to come talk about some of the emerging technologies that we are employing in our work for research and conservation. So as you mentioned, my name is Sarah Hoffman, and I am a scientist here at Biomark, working primarily in tech development.
Hi, everyone. Richie Carmichael. I'm a senior scientist at Biomark as well, working with Sarah in tech development and fish habitat relationships for conservation of anadromous species.
And Biomark is located right here in downtown Boise, so right over by the Anne Frank Memorial off of the Boise River, which is great for us since so much of the work that we do is with these local fishes. And Biomark was founded in 1990, so we're in our 30th anniversary here. It was founded by Don Park, who is a former NOAA fisheries biologist who saw the need to bring radio frequency identification, or RFID technology, to salmon monitoring. So we began as a distributor of tags and readers and services for fisheries conservation, but we've since grown to include all of our own manufacturing and development of custom systems here in Boise. We work with clients all over the world now. So we have offices, I think, on every continent, every continent except Antarctica, I suppose, at this point. And we are growing significantly in Europe, and we were recently acquired by Merck. So now we fall within the Merck Animal Health umbrella, and we are starting to work more with industries such as aquaculture. With that said, I want to take it back today and talk a lot about the majority of our work, which has occurred within the Columbia River Basin. And the Columbia River Basin is in the Pacific Northwest of the United States and Canada. It encompasses close to 700,000 square kilometers, which covers 7 states and 1 Canadian province. It encompasses close to 1,200 miles of river and is known habitat for 609 fish and wildlife species, of which there are quite a few endangered species in this region as well. One of the major initiatives within the Columbia River Basin has been evaluating the effect of the over 60 dams that occur within the watershed. And that is of major interest to us because we work primarily with anadromous fishes. And what an anadromous fish does is spend some part of its juvenile life history in the freshwater tributaries up, such as we have here in Idaho. And then it will start to make its way out to the ocean. It will spend some amount of time in the ocean, migrating around the Pacific, and then it will re-enter the Columbia River and come back up to its natal tributary, so where it was born, in order to spawn again. So it has this cyclic life cycle. And the 2 species that we work with primarily, you can see here, which is a Chinook salmon on the left and a steelhead on the right. And as I had mentioned, we see this life cycle going from freshwater tributaries to the ocean and back. And that has been significantly affected by a number of practices that have occurred with anthropogenic landscape changes in the Pacific Northwest. And those tend to be boiled down into 4 major categories, which we call the 4 H's of salmon conservation. So those would be hydropower, so the development of those dam facilities, which are a physical barrier to the migratory pathway. Harvest, we're approaching close to a century of overharvesting of salmon, which have led to major population declines. Hatchery would be the third. So in an effort to help boost some of these populations, as well as production of these specific salmonids, there have been hatchery efforts to release fish. And this has had some unintended consequences, both on the genetic side as well as the competition side. And then the 4th H would be habitat. So decades of anthropogenic changes to the landscape, such as agricultural practices or development of places like Boise. These cities along the riverbeds have significantly affected the river morphology and thus the habitat for these salmon populations. So with the passing of the 1973 Endangered Species Act, there was really a new market for conservation. And that's when Biomark really came into the game, because there started to be big federal dollars that are interested in conserving these natural resources. And with the founding of Biomark, began the era of installing this infrastructure throughout the rivers in order to track salmon movement. So as you can see in this picture, there's an antenna it's fully autonomous. So it's hooked up to a power generator. You see that solar panel, and it has a communication unit. So it is relaying data in real time as fish pass over this antenna. And the way this works is through something called a passive integrated transponder tag, or a PIT tag. It's about the size of a grain of rice, and it's actually the same kind of microchip that you would put in your pet, for example. So we started applying this type of tagging technology to fishes, given this infrastructure throughout the river, in order to track their migratory behavior, as well as get a better understanding of what the population status actually was. So about 5 years after the founding of Biomark was the founding of an organization called PITAGIS, which is the Pit Tag Information System. And this is a public data repository that created these standardized monitoring efforts for salmon throughout the area. So now stakeholders in Idaho, Washington, Oregon can all have the same standardized data collection efforts in order to get a much broader scale view of the whole Columbia population. And so with this infrastructure going into the river and with this standardization effort, we start to now have usable data that we can do these big analyses on. So one of the first analyses that happened within our group was the State Space Adult Dam Escapement Model, or STADM. And what this model did was take traditional data sources such as window counts, which is where somebody will stand at a window in the dam and count the number of fish that are passing over, as well as fish trap data. But now with the advent of pit tag technology, we have a way to monitor unique individuals moving past a dam. So the dam you see here is Lower Granite Dam, and we can get a total population estimate of every fish that is escaping or moving back into the freshwater habitat. And with this state space model and this total population estimate with a known measure of uncertainty, we can start to look at how these fish are moving into different rivers or different tributaries of the rivers. So the next model that we have worked on is the DBOM model, or the Dam Adult Branching Patch Occupancy model. And what this does is let us get a reach-specific view of species-specific and origin-specific fish. So when I say origin-specific, we're talking about the difference between natural origin fish and hatchery fish. And this is particularly important to recreational fisheries managers who want to make sure that anglers are targeting hatchery fish. So we want to conserve as much of those natural origin fish as possible. And what we can do, based on our estimates from STADM, we know how many fish are in these areas between antennas. So for example, if you look at this figure on the top, you can see that there is a relatively high proportion, almost 4 times the amount of hatchery fish to natural origin fish from Rocky Reach to Wells. So for example, or in this case, that recreational fishery would be open. You would send the anglers to that area. Whereas if you look just below it from Rock Island to Rocky Reach, you can see that there are actually more natural fish in this area compared to hatchery fish. So that recreational fishery should be closed in order to prevent the capture of any of those natural origin fish. So with this infrastructure and this modeling approach, we have the ability to really track the adult population levels throughout the Columbia River Basin. And that really helps us get at the effect that something like hydropower facilities are having on that upstream migration, as well as whatever effect maybe these harvest or these decades of harvest have had on the population as a whole. But we're still really not getting at those other life stages, which would be the freshwater life stages. And one thing that we have learned throughout decades of research and biological opinions is that freshwater habitat has been significantly degraded. So those life stages, the younger life stages that are really important for informing that adult return, is still relatively unknown within our landscape. So in order to address this, we developed our first machine learning model that was used to estimate the habitat capacity of these freshwater reaches by species and life stage in order to get a better idea of how much quality habitat is out there, what is considered quality habitat, and how can we look towards prioritizing different habitat restorations. And with that, I'm going to hand it over to Richie.
So just building on what Sarah alluded to, how we're assessing and addressing some of the limitations in one of the 4 H's known as habitat. This slide here is a nice example of how we're utilizing legacy data sets. So roughly 10 years of historic paired fish and habitat information. The fish information coming from what we call mark recapture abundance surveys, and the habitat information coming from what was known as the Columbia Habitat Monitoring Program. So the map on the left shows an output from one of our machine learning models where at each one of these points we've paired fish and habitat data to then assess the number of fish that that given location or those given locations can support for various life histories, whether it be juvenile or adult or winter or summer. We then utilize remotely sensed information, typically derived from satellites, to scale that assessment up to an entire watershed level. So this map on the right shows what that extrapolation model might look like across the entire watershed or a given watershed within the Columbia Basin. And this is a really nice technique to assess some of the limiting factors that might be present within a watershed or within a given location. So some of the traditional habitat sampling that I alluded to from the Columbia Habitat Monitoring Program, or the CHAMP program, had some limitations. Because it is nearly a decade old at this point, the program no longer exists, but we utilized traditional surveying techniques. So things that you might see out on a highway, for example, would be a total station, which is a picture you have here on the left. We utilize total stations to literally map the bottom of the river to then assess how the habitat affects these fish. These types of samples are very time and money intensive because you're paying ground crews to go out for long periods of time to sample roughly 200 to 600 meter reaches of the river. We collect anywhere from 250 to 300 unique measurements about that section of river. But like I said, that can oftentimes be time intensive. And so what we found was that we needed a new way to sort of more rapidly cover larger areas of stream. And you can see in the pictures on the right, those are 3 repeat satellite images showing how the habitat might change over time. And to keep up with this change over time, we really saw the need to address this habitat sampling limitation to pair with the fish data to improve our modeling efforts and our machine learning algorithms. So that's really where drones came into the picture. During my graduate work, I bought a drone and I started flying it and mapping rivers because I saw in the future that drones were the new technology to sort of improve how we sampled and assessed fish habitat. And so this is just a really nice way to capture complex environments with really high resolution. Oftentimes 2 centimeter pixels is the imagery that we're collecting over kilometers of stream. But that results in some bottlenecks or limitations in terms of processing. So we're working on some of those algorithms, which I'll get to here shortly. We've been able to pair not only drone and fish habitat information, but also on the ground habitat information to really complete the full circle, because oftentimes there's a lot of metrics that cannot be assessed via drone because maybe they're under canopy or under the water. And so we are able to pair a couple different unique methods to best assess the habitat. And this sort of came to fruition as the drone assisted stream habitat protocol, which is a protocol that we developed here at Biomark to sort of bring all of this together, the technology innovations, the traditional on the ground sampling, and then the fish sampling as well. So one really nice result from this type of technique is that we're able to cover much larger areas much more efficiently compared to the traditional methods. And so in this slide, you'll see that The picture to the right is actually what we call more of a channel unit scale assessment. And so we can estimate the number of individuals, in this case, the number of juvenile Chinook salmon that can be supported in a given channel unit, like one individual pool or one individual riffle or one side channel. But then we can also scale that up to a reach scale. So the map in the middle would be a nice example of a reach, which is roughly 4 kilometers long. And the way we utilize this information is if somebody's going to go do a restoration in a given watershed, we want to know what the potential or what the uplift might be for those critters. So we can assess the carrying capacity at the reach. Pre-restoration, they can go in, do some type of habitat enhancement, and then we can assess what the capacity uplift is for that given location. And for the first time, we're really able to put a monetary value on how much restoration might need to occur in order to get to a point where these species might be delisted from the ESA. We can still then utilize other remotely sensed information to roll that up into an entire watershed scale estimate. And so now we're making these estimates across the entire Columbia Basin, really starting to nail down where we have some of these capacity limitations, which then gets communicated to basin practitioners, engineers, biologists about what type of restoration might need to occur to target a specific life history, whether it be adult or juvenile, overwintering or summer rearing. We also utilize not necessarily advanced sampling techniques in this case, but oftentimes these rivers are hard to reach. And so we will use any methods necessary to get down the river. Here we're floating down the river, stopping at random locations to collect more habitat information to pair with the drone imagery and the fish data. So here's another way we utilize drones. This is a nice video flyover of one of our pit tag antenna sites. And we use these videos to communicate the technology advances and the technology that we utilize to folks that maybe might not be as familiar with what a pit tag antenna or a pit tag array might look like. And so this is just a really nice way to use the technology to show people and educate them about exactly what we're doing and how we're using the technology to improve the plight of these species. Another way we utilize drones is through 3D rendering and 3D meshes and textured meshes. So this is a great way, for example, if a restoration is taking place, you can show them the progress of the restoration without physically taking them there. It's like a poor man's virtual reality. So we're essentially using drones and photogrammetry, which is a technique to go from 2 to 3D to capture imagery and to capture 3D orientation of certain aspects within the river. So this case, this is the same site that we had the video of, but this is an actual 3D rendering where you could click in and out and zoom in and out of that location. So this figure here shows one of the first drone flyovers that we ever did. This is a wintertime sample. This is one of the first ones that I did in grad school many years ago. And it just shows how easily we can capture these complex morphological features and how they orient to each other, because this type of information is really important for explaining the experience of a fish. In this case, we have a lot of side channels, a lot of braiding, a tributary coming in. And historically, with traditional surveying methods, all of this information would not have been captured if we hadn't flown a drone and been able to really cover that large area. And we can seamlessly overlay it on satellite imagery or any other type of remotely sensed data. So it's just a nice way to show how all of this pairs together and how we're leveraging technology and forward thinking about how we can pair drones, on the ground fish, and as satellite technology improves, also incorporating satellite information. So the previous drone scan was just a simple red, green, blue camera, RGB camera, 20 megapixel CMOS sensor. So it picks up light reflectance similar to what our eyes can see. But recently we've incorporated a multispectral camera, which has red, green, blue, and also multiple infrared bands, as well as a long wave infrared thermal band. And these bands just help us in the post-processing step to differentiate between what the cover type might be within the imagery. So we need to know where the river is, where vegetation is, where wood is, where bare earth is, because all of those things go into generating metrics that are important for explaining the distribution and carrying capacity of these fishes. In addition, the infrared band, the long wave infrared thermal band, allows us to really find some of these warm and cold water refuges within the watersheds that also help explain how these fish distribute throughout the system. And this is just a nice way of showing that here in this graph. So on the left, we have a traditional red, green, blue image, and on the right, we're showing the long wave infrared, where you can clearly distinguish between the wetted channel, the vegetation, the bare earth, and the banks. And as I said, all of that information feeds into our machine learning algorithms to really aid in the post-processing of this imagery, typically doing it locally, but we're setting up a cloud computing service as well. So we're moving forward with a lot of these machine learning algorithms, whether they be pixel-based or object-oriented. So that leads me into sort of how we deal with some of these images and how we process them. So this slide's showing essentially 3 bands from a single image. As you can see, there's some discrepancies between the two. They're not topologically correct. They're not landing right on top of each other. So what we have to do is we find some common points amongst these images or amongst these bands, and we align them based on those common points. And so we can get a much crisper, more clear image. Then what we do is we run them through a histogram equalization step. So essentially we're increasing contrast. What we found is that the machine doesn't really care if it looks funny to your eye. The machine just cares that there's contrast amongst different land cover types. And so by aligning the bands and then running it through some contrast equalization or increasing contrast, we're able to pull out a lot more information and differentiate between different types of land cover classes. And so what a processed image might look like is this example here, where we've automatically differentiated between water, vegetation, bare earth, and woody debris. And this information will be further processed with some of our on-the-ground data to then start to assess how much of different types of land cover we have, how many pools do we have, how many riffles, what's the vegetation health, what's the sinuosity of the river, things like that. We can start to assess morphological characteristics as well as habitat characteristics. Oftentimes in these stream restorations, they're loading the river with wood because more wood equals more fish, equals more cover, equals more dynamic processes, equals good for fish. Oftentimes they're loading these restorations with thousands of pieces of wood. And you could imagine it would be quite the task to go out and measure and count each one of these pieces of wood with the traditional habitat sampling technique that I talked about earlier. So what we've done is we've developed a pixel-based automatic classifier, which essentially goes into each pixel of the image and finds which of those pixels are wood. So in this case, you can see the row of photos on the top have not been classified. The row of photos on the bottom, every pixel that is wood is now colored red. And what we can do is then sum up all those pixels to get a total area of the amount of wood that might be in that given location. Moving forward, we'd like to get away from the pixel-based classification just because it doesn't find individual objects within an image. It can't figure out how orientation and clustering of pixels might equal a piece of wood. It just knows that individual pixels are wood. So we've moved forward with an object-based classifier. In this case, it's a regional convolutional neural network with a masking component. So essentially what this does is it searches across the entire image and finds objects that might be wood or objects that might be part of the wetted channel or trees or vegetation. And so it can actually assess each individual pixel at the pixel level, but then it can also cluster them all together into a single object. And we've taken this sort of technology that's been applied all over computer science and engineering, and we're now applying it to riverine mapping, in this case, finding wood and finding the wetted channel. So that's what both of these images are showing. You have masks drawn across the pieces of wood and masks drawn across the channel with some type of certainty, statistical certainty associated with those. So we're having some really nice results in this sense, moving towards more of a convolutional neural network and away from sort of your more traditional pixel classifiers, which would be the random forest that I built. We've been fortunate enough to pair with some groups in the marine environment, in this particular case on the coast of Florida, where they're utilizing drones to not only track migrations, but count individuals as they make these mass migrations across the ocean. Typically, these would be black-tip sharks, manta rays, sea turtles, where oftentimes you could have upwards of 10,000 individuals in a single drone image. And so we're utilizing this object-based detection to automate location and then counting of those individuals. And that information can be used in individual dynamics if a predator approaches, or in shoaling dynamics or schooling behavior. And so we're utilizing machine learning not only in riverine mapping, but we're applying it to the marine environment as well, where historically you would have to count individuals. Now we're utilizing the machine, we're letting the machine count them, track them, create things like heading and movement rates and things like that.
I think kind of the theme of what our group is really trying to do is think about how we apply these emerging technologies that have been developed in other fields to our field. And this is kind of actually just the history of conservation. There are limited budgets, right? So we have to figure out how we can get the best data with the broadest inference on a relatively small budget. So next up, we're thinking about no, just kidding. We're not going to go fishing with drones, but not kidding. We are looking at incorporating machine learning algorithms into tags. So how can we, now we have all of this great ecological information about where there's good habitat, how we can improve that habitat, and how we can prioritize that for salmonids, or like Richie was just talking about in the marine environment. But now we have the opportunity to really drill down and see what those animals are doing in these environments, which is data that is traditionally lost. So tagging gives us a great understanding of where animals go and how long they stay there, but we really want to know what they're doing. So that's kind of the next evolution for us is using an individual-based approach to think about these broader ecological pictures. And with that, I would like to thank everybody for being here today. We really appreciate your time, and we would be happy to take any questions, or feel free to reach out to us with the emails listed here.
Thank you so much, Sarah and Richie. We do have time for a couple of questions. Eric, if you have them now.
Well, that was fascinating. Thank you very much for that. I'd love to hear a little bit about the unique challenges you get from trying to use these techniques in an aquatic environment. You know, some people who are watching this might be thinking, you know, they've seen the videos, the scare videos from China with all the green boxes around people and identifying people as they walk through the subway. And, you know, we're doing a lot of that kind of stuff. But it seems like the aquatic environment would have its own set of unique challenges and make that a lot harder. Can you guys talk about that a little bit?
Yeah, sure. The aquatic environment does present a lot of challenges. You have inherently extremely dynamic systems to begin with. You know, one of the biggest issues we struggle with is just simply being able to characterize and understand the morphology of systems. Oftentimes we don't even know, or we can't project what a river might do in the future. So that makes it very difficult to sort of take what I think a river as like a round hole and our minds as a square peg, and trying to characterize or understand what a river is going to do and how it relates to fisheries. And then you have, you know, not just that level of understanding of how a river might trend over time, but we also have physical limitations like vegetation, water turbidity, water surface turbidity. A lot of those things pose pretty extreme issues. And so one way we've combated that is we have a couple different techniques when we're trying to assess, for example, how much habitat is in a given location. We can do it in 1D, 2D, or 3D, and oftentimes going from 1, 2, or 3D can help us get around some of those issues with vegetation or water surface turbidity. One thing to note, I think that's important, is in the techniques that we've come up with, we've utilized legacy data to limit the number of habitat metrics that we need to measure to best explain how fish are interacting with their habitat. And so oftentimes you have researchers that are really focused on mapping the bed of the river. In our case, we've been able to remove that step completely, where we don't necessarily need to map the bathymetry or the bed of the river, but we just need to know some of the characteristics like slope or sinuosity or gradient or things like that. So through our statistical analysis of legacy data sets, we've been able to work around some of those difficulties in mapping rivers.
Got it. So I think it's super impressive that that you guys, you know, you're not a bunch of machine learning scientists, and I think it's impressive that you guys are using these techniques to do such important work. So I definitely appreciate that. We need to make sure the salmon populations are you know, I guess conserved is the best word.
Yeah, absolutely.
So one of the problems with sensor data in general is that depending on what type of sensor data we're talking about, and you know, you're talking about visual sensor data, from the drones at least, is the volume. So can you talk a little bit about how you're handling such a huge volume? I imagine this is even greater volume than a lot of most terrestrial applications, probably just because of the way that you have to survey and resurvey the area and the amount of time you have to do it over. And so you got a ton of data. So what are you guys doing about that? And does that have any broader applicability? Is that going to seep out of your work into the wider world to handle these large amounts of data?
Yeah, I think what we're doing is not unique to other large data problems. It's been a bit of a challenge for us because of our limited knowledge in things like cloud computing. But essentially what we did was we piecemealed it together with external hard drives for several years as we were sort of pioneering this project. We quickly realized that was not an answer. So what we did is we utilized a NAS device, which is essentially a large storage device, which we linked to an Amazon S3 bucket seamlessly to the cloud. So we're actually able to back things up locally, and then it links seamlessly to an S3 bucket, which is then automatically updated in an Amazon instance or a cloud environment. And then that's where we're able to do all of our computing. We also utilize local high-powered machines as well if we're tuning algorithms or testing algorithms. But currently we're integrating into an Amazon environment where we're able to have a backup, have a seamless link to the Amazon environment, but then also able to get our software and our code up onto the Amazon environment to run some of those algorithms and do the testing and do the storage. So it gives us two separate sort of environments to store the data independently.
Got it. And so I guess my final question is, where do you see all this going in the future? What's on the slate for making improvements to the way you're doing this, or adding sensors, or whatever that is?
Yeah, so I think that's a great question. And it's pretty broadly accepted throughout the wildlife community that drones are a really effective way to get population level estimates all the way down to individual measurements of behavior. So we have this sort of nebulous idea that this technology exists and should be applied to our industry. However, as you mentioned, the volume of data and the complexity of that data that you gather is often cited as a barrier to entry for the use of drones in conservation. So our goal is to develop these tools that are broadly applicable throughout the research community, throughout the conservation community, so that we can start to see the implementation of drones in wildlife management and conservation purposes, to see this broader adoption of the technology. As Richie was mentioning earlier, the costs associated with going out and ground sampling, sending a whole crew out with expensive equipment. Oftentimes these areas are also hard to reach. They're dangerous to reach. We know that surveying in helicopters and airplanes is particularly dangerous as well. So drones are this sort of pie in the sky ideal solution that we have. We just have to figure out really how to nail it down to take that imagery and turn it into actionable data that has meaningful consequences for these managers.
Yeah, and just to add on to that a little bit about where we see it going, I don't think we're far off from replacing drones with satellites. I think that the sensor packages on satellites are going to get so good that you might not need a drone anymore to get that sub-centimeter resolution ground sampling. So I think once we have the infrastructure in place to house not only the data, but also automatically generate metrics, not too distant future, we're probably just going to be utilizing satellite information when the habitat or the scenario allows us to do so.
Fascinating. Well, thank you for answering my questions, and thanks for talking to us today.
Absolutely. Thanks for having us.